Hello.
Sir, good morning, sir.
Nangari. Morning.
Good morning, sir. Morning.
Thank you.
Sir, start ചെയ്യാമല്ലോ അല്ലേ സർ?
നമ്മൾ 11:15 പറഞ്ഞേക്കുന്നത്.
അതെ സാർ, ഇപ്പോഴേ സ്റ്റാർട്ട് ചെയ്താൽ നമ്മുടെ വെൽക്കം കഴിഞ്ഞ് നോർമൽ ടൈമിൽ സ്റ്റാർട്ട് ചെയ്യാം.
ഓക്കെ, എന്നാൽ തന്നെ തുടങ്ങിക്കാം. ഇല്ല, നമ്മൾ സമയം പറഞ്ഞു കഴിഞ്ഞാൽ സമയത്ത് തന്നെ തുടങ്ങാവുള്ളൂ. അതുകൊണ്ട് ഞാൻ പറഞ്ഞത്. കേൾക്കുന്നു നല്ലോണം.
ഉണ്ട് സർ.
ഹലോ, ഗുഡ് മോർണിംഗ്. വിനീത്.
സർ.
ഹലോ വിനീത്. ഹലോ, ഗുഡ് മോർണിംഗ്. ഡോക്ടർ വിനീത് കേൾക്കുന്നോ? വിനീത് കേൾക്കുന്നുണ്ടോ?
എനിക്ക് കേൾക്കാം.
ഇന്ന് ഞാൻ നാസറാണ്, പ്രിൻസിപ്പളാണ്. മോർണിംഗ്.
ഗുഡ് മോർണിംഗ് സർ.
എവിടെ വീട് എവിടെയാണ് നിന്റെ?
എറണാകുളത്ത് പനങ്ങാടെന്ന് പറയും. പനങ്ങാടെന്ന് പറഞ്ഞാൽ നമ്മുടെ ലേക്ഷോർ ആശുപത്രിയുടെ അടുത്ത്.
മനസ്സിലായി. ഞാൻ അവിടെ എറണാകുളത്ത് സ്ഥിരമായിരുന്നു കുറച്ചാൾ. എന്റെ മോൾ ഇടപ്പള്ളി. എന്റെ മോള് ഇടപ്പള്ളി താമസം ഉണ്ടായിരുന്നു അവിടെ മെഡിക്കൽ കോളേജ്. മറ്റേ അമൃതയിൽ ജോലി പഠിക്കുന്ന സമയത്ത് അമൃതയിലും അവിടെ ഹസ്ബൻഡ് PG പഠിക്കുന്നുണ്ടായിരുന്നു. സ്ഥിര സ്ഥലമായിരുന്നു. ഓക്കെ, നമുക്ക് തുടങ്ങാം. സമയം തുടങ്ങാം. ഓക്കെ, ശരി. സഹീറ തുടങ്ങിയോ?
Good morning and welcome each and everyone to today's webinar on the topic Data Analytics, Exploiting the Power That is Data, being conducted by ICAM, the Students Association of Computer Science and Engineering, Mesitam. I, myself Naja Fauzi of the department, and I'm excited to be hosting the section. First, I request our head of the department, Professor Sahir Raj, to render a brief word of welcome. Please, sir.
Thank you, Naja. Hello, everyone. Good morning. Respected Principal Dr. J. Nasser, most respected speaker Dr. Vineet, HOD Jyoti Engineering College at Thrissur, dear participants, both from our colleges and both in-house and from other colleges. Good morning, one and all. I am very happy that we are at the brim of commencing the next webinar session in our webinar series. Actually, ICAM, the association, is planning a series of webinars, and we are at the next webinar. Okay, and I'm not talking in detail about the past of ICAM. After the commencement of ICAM in 2012, it is very active in the college, and I wish the association a success in future also. Okay, today my duty is to welcome the gathering. I'm not wasting the time, and I'm directly moving into my duty. First of all, I'd like to welcome our principal, Dr. J. Nasser, the backbone of our institution, to the section. Welcome, sir.
Thank you.
Next, I'd like to introduce our key speaker, our speaker, Dr. Vineet, HOD Jyoti Engineering College. He had done his MTech in computer vision and image processing from Amrita Vishwavidyapitham, and he had done his PhD in the area pattern recognition and machine learning from NIT Calicut. He worked as adult faculty in NIT itself, and presently he is working as the HOD at Jyoti Engineering College, Thrissur. Actually, he had done various funded projects. He had presented many papers in various journals and conferences, and we are very lucky that we got a good presenter today to handle this session. Okay, I'm not taking more time. Actually, I also would like I welcome Dr. Vineet to the session. Okay, I'd also like to welcome. I'd also like to welcome HODs of other departments and the faculty in-house and those from other colleges, as well as the students, participants, both in-house and from those from other colleges, to the session. I hope you all get a very good time in this session, and you'll get what you expect from this session. Okay, I wish this session a very success. Thank you.
Thank you.
Thank you, sir. Now, I welcome Dr. J. Nasser sir, Principal of Mesitam, to address the gathering.
Thank you, Naja.
Welcome, sir.
Chief Host of the day, Dr. Vinny Dar, Head of the Department of Computer Science, Professor Sahir, student coordinators, my beloved students Ashwin, Abhishek, and Naja, faculty members, staffs, and my dear participants. A warm good morning to one and all. I am extremely delighted to participate in this webinar organized by Computer Science Department. I greet warmly our chief guest of the day, Dr. Vineet, and all other participants to this webinar. I think this webinar will be an insight to the recent developments in this area and definitely enhance the depth of the participants. Depth of the knowledge of the participants. I would like to congratulate the coordinators of the departments for organizing this. I wish the very best to our chief guest, Dr. Vineet, and all other participants. I hope a wonderful section ahead and all the participants can enjoy. Thank you all. Thank you once again. God bless you.
Thank you, sir. It's great to have Dr. Vinny Dar, Head of the CSE Department of Jyoti Engineering College, Thrissur, here with us today. Dr. Vinny Dar has PhD from National Institute of Technology, Calicut, and has specialized expertise in computer vision, image processing, and machine learning. His research interests includes applied ML, deep structural learning, travel pattern analysis, and so on. He has served as resource person for faculty development programs and workshops in various institutions across Kerala. So without any further ado, I welcome Dr. Vinny to take over the section.
Thank you. Thank you very much. First of all, am I audible?
Yes, sir.
To
Yes.
Okay. Thank you. So first of all, let me congratulate the organizers, the department and the college for organizing. So it's nicely organizing such a program and inviting me. And also I thank for having invited me to this session. So as an introduction, let me just tell you that I have been instructed to give you a very fundamental, introduction to machine learning as to what exactly do we actually do in machine learning. What is it in fact, and then what are the possible areas where students can develop their skills in so that they get themselves employed in some companies or industry or research institutes which employ data analytics as their for their various processes. So my presentation, actually my talk, I have basically divided it into two parts. The first part will essentially deal with what is machine learning, what are the skill sets that are expected of an ML or a data analyst or an ML engineer, and what are the different aspects of data analytics as a whole. And then in the second part, I was actually, Surimi Miss wanted me to present a certain practical hands-on on how machine learning algorithms are implemented and how we, given some data, how we perform analysis of that using various algorithms and what are the different techniques that we use. Very fundamental things will be discussed. So let me just start my presentation. I'll switch off my video camera and then move on to presenting my slides in the first place, and then move to the hands-on session. So let me just start with my presentation. Is my presentation clear to you?
Yes, sir.
Okay, fine. So I'll just start with what is machine learning, what exactly as a branch of computer science, as a branch of computational discipline, what exactly is machine learning? Machine learning, as you all know, you might all be aware of what I've just written here. It is basically the study of algorithms which are self-adaptive. Okay, so you give it more experience, it becomes better at performing some task. So there is the key idea behind machine learning is to learn about algorithms which adapt themselves to more of experience, and so that their expected output becomes better in terms of quality. So there are key things about this statement is what exactly do you mean by performance? What exactly do you mean by task? And what exactly do you mean by experience? So generally by performance, what we mean is it depends. It's the performance is basically a problem dependent or specific term. It depends upon the kind of problem that you're trying to address. For example, you are dealing with, say, predicting the stock prices. You should be, expressing performance in terms of the error that it makes. So the idea is that the lower the error, the better the performance. You can mathematically or quantitatively express that in terms of some kind of an error measure. For example, something that we all know of is the squared error between what you predict and what is actually happening. So that is basically what you call performance. Improve the performance, you reduce the error in that sense. Or if it is a classification task where you want to categorize data, you probably will be looking at the accuracy of classification. The better the accuracy, the higher the accuracy, you say that the algorithm is performing better at the task, and the task there is classification task. And what exactly do you mean by experience? Can somebody tell me what exactly do we mean by experience in this context? Okay, can somebody tell me?
The repeated learning.
What exactly do you mean by repeated learning?
Seeing a thing again and again and studying about things.
Yes, not studying about the system cannot study anything. I mean, you just have to do everything for the system. With experience, what we essentially mean is the most important part of that is repeatedly seeing data, the same data over and over again is one aspect of that. And moreover, to see more of data, to give it more of data to work on. For example, you want doing a classification task, and you want to, for instance, classify images, say an MRI scan into a normal scan and a scan with, say Alzheimer's disease. You want to categorize that. So that is the purpose of your algorithm. So you give it more, data, the system will become better and make more informed inferences from an MRI that is given to you. By experience, what he essentially means is legacy data or historical data that you have collected about the problem that regarding in connection with the problem that you are basically trying to solve. So you give it more data, the system adapts itself to perform better. That is, and those classes of algorithms. This class of algorithms is generally what we call a learning algorithm. So, and it's different from the traditional way you do computation. In traditional algorithms, you give data as input to the program, and you process it and produce some output. Okay, that is what you give. Okay, the program is fixed. The program doesn't change. So you give input and you take an output from it. That's how the traditional program works. But in the machine learning algorithm, what you basically give to it is you give the input and also the desired output. Okay? You give the input, you give some input, and you say this is what I want out of it. Then, so therefore, you give the input-output pair to the system, and the machine learning system basically develops a program which connects this input with your desired output. So here it learns the program rather than the program being fixed. Okay, so that is basically the idea of adapting itself to the problem that you are basically giving it. Okay, so that's the very fundamental and philosophical difference between the two: the traditional way of solving problems and the machine learning way of solving problems. So, and there are certain problems which can solve only in the machine learning way, because there is no other solution to that. For example, you have three images of three cats, and the idea is to say that an image, the image of a cat, should be called a cat's cat, and the image of a dog has to be called a dog. Given the input, it should be categorized as cat and dog. You cannot write a static algorithm which doesn't change, which doesn't adapt itself, which doesn't change any of its parameters to do this task for you. You cannot write if-else statements to do this. You cannot have rule-based solution for this. It's very hard, or rather, I would say impossible to do something that, works that way. The only way to solve this is to look at it in the way humans basically learn. So ML, in a way, it mimics how humans learn things. How does a child learn the image of a cat? You continually expose the child to various images of cat, and after seeing a number of images, maybe the child's brain somehow figures out the significant characteristics of the animal called cat. And then when you see a new image or a new animal, the child's brain, what it does is it checks if those features are actually there, and based on that, it says whether it is a cat or something else. This is precisely the way the organic thinking basically happens, and this is exactly probably the only solution for solving problems of this sort. And it is precisely this that machine learning attempts to do. So what I would say, what I was just trying to put across is that there are some patterns in the images that help humans recognize them as cats. Okay, so our brain automatically does that. Our brain is so much capable of extracting those patterns from the images so easily. And given a new one, we can easily say whether it is a cat. Okay? It's precisely those ideas that we are trying to translate into programs, though may not be an exact mimicking of the biological neural processes, because it's very hard to mimic the biological neural, because there are so many very, very complex, processes happening underneath. So therefore, what we basically try to do is we try to have very simplified modeling of those processes maybe, and not always, I would not say that every machine learning algorithm is a mimicking of, those those biological processes, but it takes some cues from those things. What ML does is it tries to understand the patterns from the image. Okay? What we do is we write algorithms that automatically figures out those patterns, just as the human brain does. It automatically figures out those patterns. And then when a new image comes in, it looks for those patterns and then categorizes it. So that is the idea of machine learning and how it differs from a traditional, conventional computational algorithm. Am I making myself clear up to this point?
Yes, sir.
Yes, sir.
Right. So in that way, we are essentially mimicking the way a child learns to recognize a cat from a mouse. So the process is basically to figure out patterns, to figure out the relation between input and output, all by itself. Right. Okay. We just create a framework. What we programmers do is we create a framework wherein the system will be able to adapt itself. We lend the system a certain degree of freedom so that it can adjust itself with the input and output and develop an algorithm of its own. Okay. So what we essentially do is we give the algorithm some images of cats and tell it to figure out what makes it a cat. And this process is what we call learning or training. And the images we give to train the system is called training data. These things might be quite familiar to you. Human and the difference between a system and a computer system and human brain is that the biological brain needs very meager amount of images, very low number of images to figure out those patterns, whereas you will need a huge number of images for the system to figure out what those critical features are. That is a fundamental difference between the biological system and a computational system, a machine learning algorithm. So how does the machine basically do this? Can somebody tell me how is the input and output related to each other? I mean, how does the system manage to do this? Can somebody tell me?
A mathematical equation.
Yeah, somebody I think gave me an answer. What was that, sir?
It's a mathematical equation.
Exactly. So you basically model the output y as a function of x. Okay. And where is the learning coming into picture? That is a simple computational model. But what is the difference between a simple computational model and a learning model?
We are giving some weightages, numbers.
What exactly are those numbers?
I don't know exactly the numbers, but we are by training the system. What we are doing is we are changing the certain numbers in a complex equation, and we need some result according to what we are giving. So what we are doing is we are changing a complex set of numbers to our need to find out a problem, to find out a solution for some problems like image sensing, image recognition, etc. stuff.
So basically, I think you're almost at it. So what the idea is actually very simple. The idea is that you have the input y, the input x, which I think I have. Can you see the highlighted portion that I have done here?
Yes, x.
Yeah. So that is the input, and say you have the output y. Okay, you have the output y. So what we basically do is basically the system is a computational device. It can just do mathematics and computations and nothing else. So whatever those philosophical ideas that I have been telling you have to be ultimately translated into mathematical models for the computational system to work. So therefore, what you do is you think about a mathematical function that connects the output y with the input x. And so therefore, y can, for example, be equal to x plus 5. That is one relation, right? Y and x are related by some equation or some mathematical analytical function. Here, the difference is that you have something called theta that I have written here. Theta is exactly what I think Sir was referring to as numbers. They are called parameters. You adjust theta such that for a given input, the output that the function produces is as close to your desired result as possible. Is that clear? Is that idea clear?
Yes.
Okay. You adjust theta such that when you give an input x, the output that the function produces is as close, in some sense, I would say, in how close, the definition of, how close it is, the idea of how close something is y to what f produces has not been defined properly, but I'm giving a very intuitive idea of what exactly learning is. F is the function. You give f, and it has a set of parameters theta, and then you give x as input. It produces an output y, and you want this y to be as close as what you want it to be. So how do you do? What is the only thing that you can change? The only thing that you can change is the parameter. You change the parameters of the function f in such a way that the output becomes as close to what you desire as possible. Okay? This adjustment of parameters is precisely what you call as learning. Okay? I'll give you an example of how this. I'll give you right now itself so that you can understand it better. So, for instance, let's take can you see a blank page appearing on the screen?
Yes.
Okay. Let's say, for example, you say that y is, I said, f of x theta. Okay. An example of this could be, say, y is equal to ax plus b. Right. Here, you say, this is the connection, this is the relation. Okay, this is the function. X, of course, is here, and then theta is a and b. They are called the parameters of the model. They are called the parameters of the line. Okay? Fine. So, is that idea clear now? The idea of theta, parameters, is it becoming clear now? So, you choose an analytical function, and those analytical functions have certain parameters. If it's a line, for instance, a and b become the parameters. You don't know what the exact value of a and b are, but you have to find that out. For that, what you do is you choose say some x values which you know and their corresponding y values. Say this is how the data lies like. For every x, there is a corresponding y. For every x, there is a corresponding y. So you have a certain set of points. Based on these points, which is the best line that can probably explain this? The best line that can explain this is something like this. This is the best line, right? Fine? Is it okay?
Okay, sir.
Is it okay, sir? So what I'm just trying, you have a model and then you have a set of parameters. You try to find out, here you want to find out A and B. A and B corresponds to the parameters of this line, because this line is the best one that approximates the data, that is as close to the data as possible. Okay, so that is basically the idea. So you play around with the A and B and finally figure out that, okay, this A and this B corresponds to the best one. Because then all the points that you have chosen are actually very close to the line, so the error is going to be very low. So therefore, I can say this is a neat approximation of this. And figuring out this A and B is exactly what you call learning. Okay, so what are the aspects? How do you basically do this? You do this by defining, first of all, you define the model. In this case, it is a line. And then, based on the line, you define a model. Here in this case, it's a line. Okay. Then check if that particular, choose some A and B, choose some A and B, and then figure out how good it is. For example, your line could be something like this initially. This could be your first A and B, which is actually very bad because the points are so far away from it. Right. So far away from it. Therefore, this is not a good choice of A. You adjust A so that the line becomes as close to the points as possible. And you can measure, for instance, in this case, you define a cost which measures how close the line is to the points. The cost can be, for instance, written as the actual y for each x minus ax minus b whole square. So this is a measure of how close is a point. This is the actual y coordinate of each of these points, and this is the x, and the ax plus b is what the system predicts. This is the prediction. So how close is the actual y to the prediction? That difference squared is, you call it a cost. You change A and B in such a way that the cost is as low as possible. Choose A and B such that the cost is over the training data is as low as possible. So this is a common, process that is done for every machine learning model. You choose for every machine learning procedure, you define a model, you choose the parameters, you know the parameters. You start with some parameter, define a cost function to see if that parameter is good enough. If not good enough, then you adjust the parameters to get a better, model. You do this a number of times and finally figure out the right set of parameters where the error or the cost becomes as low as possible. This is typically how a machine learning algorithm is developed. Okay, and learning is about figuring the right set of parameters theta. So, and as I have shown here, ML is in fact a sub-branch of artificial intelligence, and now almost the whole of machine learning has been rather reduced into that of deep learning, which is a buzzword these days, which is an advanced version of the very old, artificial neural networks. So, and there are different types of learning. Learning happens in different settings. Supervised learning is what we have already seen, where you have legacy data, and based on the legacy data, you develop a system which is able to connect the input with the output. Then there is an unsupervised setting wherein you don't have any legacy data available with you. You have to extract information directly from the data. And the third is reinforcement learning, wherein there is no exact definition of what is wrong and what is right. But every time the system does something, the environment gives it gives back a feedback, and based on the feedback, it adjusts itself. So, and why is there so much buzz around ML? There are many reasons why ML has become so popular nowadays. The first one is, as I told you, ML is an algorithm which improves its performance with experience. And experience is essentially data. The more legacy data, past data that you give to the system, the more amount of cat and dog images that you give to the system, the better will be the system in classifying a cat and a dog, in separating the images. So, for that, therefore, for very complex machine learning systems, you need virtually huge amount of data. And so now with the advancement of technology and such immensely large spectrum of different data sources, data has become so easily available nowadays. And virtually data comes from possibly everywhere around you. Your mobile device is a generator of data. The hospitals are generators of data. Railway systems are generators of data. Different kinds of data are being generated on a second-by-second basis. And therefore, data has become so cheap and so easily available. And so as the data, becomes more and more available, the natural extension of this is that you need to have more powerful computational systems which can do, the storing and processing of this much amount of data. So the computational power has increased, has even quadrupled or multiple, exponentially grown over the last few years. So therefore, you produce huge amounts of the data. There is enough hardware and capable hardware to basically, process them and store them. And the third is the most important thing why ML is so popular nowadays. As we have seen, deep learning is the most common paradigm that is used nowadays. And those algorithms are quite peculiar in that typically the conventional machine learning algorithms generally improve their performance as you give more and more amount of data. But after a certain extent, a certain level, it just gets saturated, and then its performance does not typically improve with further more data. So, giving more and more data typically almost in conventional systems, mostly did not lead to a corresponding improvement in performance as more and more data is sucked in. So there is a level of saturation beyond which there is not much of a change. But deep learning algorithms are so flexible that you pump in more data, the better it always becomes. It always gets better with more amount of data going in. So that is, or you can just work in very small variations of the existing ones wherein there will be good improvement. So it is always something that typically as you pump in more data, the algorithms, deep learning algorithms, get better and better. That is very peculiar to, deep learning models. And not only it gets better with more and more data, you need also to have very efficient algorithms, new computational technologies, and efficient ways to deal with enormous quantities of data. So when it comes to huge amount of data, typically these whole data is not processed on a single machine. There has to be a distributed way of processing and developing algorithms, which also parallelly grew with the rest of the technologies, and therefore we can always distribute and store in different nodes, process in different nodes, and collect data from them and make inferences. So the development of many of these models typically happen in a distributed manner. So the corresponding computational technologies that provide efficient ways to deal with this enormous amount of data also has come up. And therefore that is another reason why ML has become so popular. Data analytics has become so popular. Along with that, you have cloud services which make high-end computational facilities accessible to normal without much of a funding. You can, you don't have to spend so much to access these high-end computational and storage facilities like Google Cloud Platform or Amazon Web Services or Azure, and so on. So, and it is gradually, progressively becoming cheaper. So these are some of the reasons. I mean, I think the main reasons why ML and data analytics have become so interesting nowadays. And the other major aspect is that most of the problems that we deal with, especially in the business community, they cannot be solved in any other way. They need an intelligent and a machine learning solution to them. There is no other way to solve many of those problems. So, as I was just telling you about, there is a huge amount of data. This is also something we typically call the big data. Big data is high velocity data, generated at a very high rate, a huge amount of data, and the structured, unstructured, semi-structured kind. These are things I think you should also be doing. So, and this is a typical data analytics life cycle, where in the first phase you first learn the data that you have, what exactly you want to do with that, what are the tools that are available to you, and so on. And then you prepare the data, that is, you do some pre-processing on the data to make it good for doing analytics, wherein something called feature extraction, noise removal, etc. are done basically in the data preparation phase. And then model planning phase, you basically choose the model that you want to build on, and then you do develop the model where, for example, you choose a linear regression model in the model planning phase, you build the model using the legacy data that you have, and once you have developed the model, you communicate the results to the stakeholders to get their feedback. And finally, the feedback is good enough, then you finally operationalize or deploy the model onto some real-world products. This is typically how you apply, data analytics in the industry scenario. And there are a huge amount of day-to-day applications, virtual personal assistants, traffic predictions, recommendation systems, Google Translate, online fraud detection, so many, innumerable number of them are actually robotic surgery, drug discovery, and so on. So, so for the students' side, what are the main skills? This is something that many people basically ask me. What are the skills expected in an ML engineer? If you want to be an ML practitioner, there are certain essential skills that are expected of you. You should be knowing certain fundamental libraries which are available in Python. Python is the most popular tool nowadays. So most of the algorithms, most of the techniques in machine learning, you don't have to implement them from scratch because they are available in various toolboxes, Python toolkits. So you have to be aware and be able, proficient in using them. One of them is scikit-learn. I will show you an example where a small, model is developed using scikit-learn. And if time permits, I'll show something on PyTorch also. Scikit-learn is a machine learning toolbox where most of the algorithms that we come across have been implemented there. And these three basically are libraries for developing deep learning models and artificial neural network models, which are modeled as graphs connecting various nodes. TensorFlow, you need not know all the three. You'll learn either TensorFlow or PyTorch or MXNet. For me, PyTorch, I'm more familiar. I don't know TensorFlow at all, so because I think PyTorch is closer to NumPy, and a person with a certain degree of NumPy background, PyTorch and MXNet both are likely to be easier. So MXNet is what AWS mostly use, and PyTorch is a product developed in Facebook. So most of their intelligent algorithms, basically Facebook algorithms, work on PyTorch, and AWS, Amazon systems, basically work on MXNet. So there are nice materials available for both of these. Matplotlib is a plotting library just to visualize the various things. I mean, you want to plot the data and so on. And so far as languages are concerned, Python, I would say, is almost an inevitable component of a machine learning engineer's toolkit. And therefore, you should be knowing Python. There is no other good but to learn Python. Coupled with that, it is always nice to know another fundamental programming language, especially if either Java or C++ would be a nice combination. Julia, I would say, is not a very necessary thing. It's an upcoming language. It's likely to get popular in the coming years, but you can, for the time being, afford not to learn Julia. I mean, ignorance of that is, of course, not a problem nowadays. But you should be knowing Python. Then one of the fundamental programming languages, Java or C++. If you are interested in a functional programming side, and especially if you want to work on certain platforms like Spark, Apache Spark, then Scala would be a programming language that would be very helpful. But Scala is not very easy to learn, whereas Python, Java, and C++, they are quite easier and for especially beta computer science students to learn. So make for a student at least two languages, Python and one of those fundamental programming languages, Java or C++, might be a good combination for you to learn. And another aspect of this is people who are not quite having a penchant for machine learning and statistics can look for other areas also of data analytics also, right? There are where they can actually go learn platforms like Hadoop and Spark, and also new generation databases, which is an area where people can really work on and develop their skills. For example, a good database administrator working in the NoSQL side is a skill set which is very much in demand in the industry. So people who are generally, for my students, typically when they come to me, if you're not good in machine learning, if you're not quite confident about machine learning, rather don't not go for that. Rather go for something which is more like the conventional computer science. You can go for a database systems, in distributed database systems, learn developing and designing, distributed and new generation database systems, so that you can that is something that is going to fetch them a decent job, and that's the reason why I want them to do. So there are various roles like ML engineer, data architect, data scientist, and data analyst, which an ML engineer basically can work on. Here, especially as a data scientist and a data architect, there comes the idea of MySQL and NoSQL databases like Cassandra, MongoDB, Neo4j, and so on. So if you are familiar with the distributed platforms, the MapReduce computational paradigm, and also the NoSQL databases, then that would be a very big value addition as far as students are concerned, and they are very likely to end up in a recent position somewhere. These are the various fundamental things. Now let me just go to a practical way in which I'll just start to work on one or two simple problems which will try to explain how the fundamental things that we have learned about machine learning, like choosing a model, defining a cost function, and then ultimately figuring out the right solution for this. Let's see how basically that is done in a small hands-on session. In a small practical way. Some small programs that I have written for explaining how things basically work. I'll start with a regression problem. Is this Jupyter notebook visible to you?
Yes, sir.
Regression problem. Is this Jupyter notebook visible to you? Okay, shall I proceed?
Yes,
Yes,
sir.
sir.
So basically, I have a linear regression problem. A linear regression problem, as I have told you in this case, I have a set of data. First of all, I'll introduce the data. It's a standard data set. It's a pretty old data set. In fact, it's called the Boston data set, where you have certain, I think, 13 features available. The first one, for example, is the per capita crime rate by town. Zn is the proportion of residential land zoned for lots over 25,000 square feet, and so on. There are some 13 such, features available, and what you have to predict is the median value of an owner-occupied home in terms of $1,000. 5 means it's $5,000. 50 is it's $50,000. Okay, so you want to predict this target variable. MEDV is the value of an owner-occupied home given these 13 parameters regarding that particular building. Okay, you know the town and you know the crime rate there. You know the percentage of lower status of population. For example, accessibility to radial highways. All these parameters are given to you. What is the probable value of a home in such a locality? This is basically the problem. So you want to predict a value. Okay, is the problem clear?
Yes, sir.
Is the problem? Okay. So, first of all, let me just show you the data set. So there are 13. You call these 13 features. There are 13 features associated with CRIN to LSTAT. There are 13 features available, and that is available in this scikit-learn data set. So here I have just imported that here. It's a Python import statement. You can basically what I've done is I have imported the data set. Okay, I've imported the data set. I'm basically loading it here, just loading the data set, and X is the input features and Y is the med value. I have 506 instances past data available with me. I have 506 instances. For example, I would say print X 0. So please look at this. So these are the values of the 13 parameters that I have been telling you, and this is the value of the house is $24,000. Okay, does that make sense? I mean, these are the 13. This is the first row indexed by 0. So this corresponds to one house. There are 13 features associated with the house, and it has a value highlighted here. So that is the output variable. We want to predict the Y variable. Similarly, if you put 1 here, you'll be getting the second, how the data regarding the second house. So you have again 13 features available here, and then $21,600 is the the house of the price of that house. Okay. So now when you get data, what is the first thing that you do? What is the first thing that you do? What is the first thing? Can somebody tell me what is the first thing that you do? Pardon me?
Select a model. Selecting a model.
No, the first thing that you should do is to clean the data. Your data might not be always, we'll be having a lot of problems in that. For example, when you collect the data, you might not be getting the value of certain features when you actually do that. There will be a lot of missing values in the data. For example, sometimes going to a particular town, you might not be able to collect the crime rate there. So for a particular home, you have not filled in the crime rate attribute feature. So there is a missing data, an instance of that. Okay, at some place, some other parameter might not, you might not have been able to collect that data. So in which case that becomes a missing feature. So the first, there are sometimes some data that you have collected might be way out of the correct value, way different from the correct value, in which case you have to correct that also. So there is something called a cleaning process before you start using the data. Okay, the first thing that you do is, the first and foremost thing that you do is to check for missing values in the data. So typically the missing values will appear as NaN. This is NP is NumPy. NumPy is an array processing library. And by the way, when you learn Python for a machine learning or a data analyst, NumPy is package is library is a must. I would say that is the single most important package as far as machine learning or data analytics is concerned. So you should be knowing that. So NumPy.nan is the value that typically appears for missing values. So you check for missing values. There are various ways in which you can fill the missing value. One strategy is to fill it with the mean of the, see, you have in the third feature, you have a missing value. One way to fill in that, you can fill it with the mean value of that particular attribute. For example, the crime rate. You have a missing position somewhere. Fill it with the average crime rate over all the towns. That is one intuitive way of doing that. Or you can fill it with a median. You can fill it with a mode. I mean, so there are many ways of doing that. So what I have done is I have filled it with the mean value. So here, simple imputer is basically data imputation is done, wherein the data cleaning, missing value filling in is done. So what I define, this is a class. Simple imputer is a class. I'm creating a class object. It's a class, creating an instance of imputer. Then imputer fit transform is given X. You basically fill in with the data, clean the data, fill in with the mean value, fill the missing entries, the mean values. This is what happens here. And now you check if there are any missing values in this, or there is no missing value, because missing values is equal to 0. That means there are no more missing values. So even you might not be able to understand each and every programming statement that I have written here, but please understand at least the process which is happening. So when you're given data, always clean it. The first thing is fill in the missing values. If there are missing positions here and there, fill in with that. Then what you do is you do something called a scaler. Okay, scale the data. Scale the data is to bring it into a normal distribution. Bring it into a zero mean variance 1 data. That is, make it zero mean unit variance, 1 variance data. So can somebody tell me why do we scale data? Why do we scale data? Can somebody tell me why do we scale data? These are all part of pre-processing or cleaning of data. First thing that you do is you fill in with missing value.
Is it a process of initializing or something?
No, it is not about initializing, ma'am. It's just about, say, for example, there are different features. One is crime rate, One is the percentage of low-income people in your surroundings. One is the distance to the nearest highway. Okay, right? Distance to nearest highway might be expressed in terms of kilometers, for instance, right? Okay. So typically the value will be 1 kilometer, 2 kilometer, 3 kilometer, and so on. So the numbers are 1, 2, 3, and so on. Okay. Whereas the number of crimes, that usually is expressed as a number. Say 100 crimes in the town, 1,000 crimes in the town. So it is a much bigger number, 100, 1,000, or 500, 600, whereas the distance is single digit numbers, 1, 2, 3, and so on. You see that they are in different scales. Their magnitudes are so much different. Okay? Their magnitudes are so much different. The distance is in 1 kilometer, but you just look at this. A distance of 1 kilometer and a distance of 2 kilometers, that makes a huge difference. Whereas a town where 200 crimes have been committed and another town where 220 crimes have been committed, they don't make much of a difference. But the difference there is 20. The difference here is just 1, but that 1 is more significant than the 20 in the other place. The reason is the difference in scales. The 20 is a small number in comparison with the values and the magnitudes, whereas the distance of 1 virtually doubles the distance to the highway. So you don't want such kind of variations in the data. You want everything to be around 0, and the variance, the distance from that, has to be of the range of 1. So you basically normalize it to the range 0, mean 1 variance. Otherwise, the system will be confused. So 200 to 300 crime rate difference, sometimes it doesn't make any change in the final outcome. But a change of, say, 1 to 2 in the distance part makes a huge difference. I mean, that is confusing as far as the system is concerned, and therefore we don't want to confuse the system. So in that way, so normally you normalize the data to 0, mean and variance on range. So I have defined again, standard scaler is a class. I create my scaler, which is an object of the standard scaler instance. And then what I do is I basically use that to transform the data. I'm basically creating an instance of scalar, and then I basically transform it. And now you can see that the mean of every column here is 0. I mean, it's not exactly 0. You don't expect anything to be exactly 0, exactly 1, and so on. It's very close to 0. It is 10 raised to minus 17, 10 raised to minus 16, 10 raised to minus 14, and so on. So therefore, it's pretty close to 0. So therefore, you have basically transformed the data to make it 0 mean. And you can also check for, if you want, you can check for the standard deviation over the axis, and you will see that again is going to close to 1. Now, what you do is, now having done all this, you have pre-processed your data, you have transformed it into a 0 mean, 1 variance data, you have brought it down to the same range for every attribute, every feature, whether it is crime, whether it is the percentage of low-income people, whether it is something else. You brought everything to this range, so now all the variables look almost the same. And now you have whole data. You have actually 506 observations with you. 506 observations with you. Let me just see here. Yeah, you have 506 observations with you, out of which what you're going to do is to use some. You don't use all the 506 observations to train your system. Rather, you use only a subset of that to train your system. The rest of it will be used for testing your system is actually performing well. So you split it into 2. a training set which will be used for developing the system, and another proportion of the data which will be used for testing whether the developed system, the learned system, the trained system is actually working. Okay, so that also is pretty easy to do with scikit-learn. There is something called train test split, which automatically, given the data, it will split it into two portions and give it to you. What I have done here in this case is I have chosen X and Y. X is the input attributes and Y is the target output that we want. Y is going to be expressed as a linear function of X, and then we want to find out what that linear function is. And then you have the whole X and the whole Y is given as input, the train test split, and I have chosen a ratio of 0.3, which means 30% of the data, 30% of 506 will be going to the test set, and 70% will be used for training. So you can see X train, X test, Y train, Y test. I think the variables basically tell you what is the output and what is the input. This is the X train and X is the training input. Y training is the Y training output. X test is the testing input. Y test is the testing output. So you can just check. There are 354 of them gone to the training set, which is 70%, and 152, which is roughly 30%, has gone to the testing set. Okay. Dot shape is the number of rows and columns. Number of rows is the number of instances, number of cases, number of data that you have chosen. 13 is the number of features. For every observation, there are 13 features, from crime rate to the other 12. So now what you have done is I am basically creating a linear regression instance. This is a linear regression instance. And I just in scikit-learn, the beauty is that it all fits into the same framework. You want to do something, you create an object of that, and you just call the fit or fit transform. There are two functions typically. One is fit and the other is the fit transform. So you are basically training here. This function does the training, the model. That's fine. To fit. Okay. So this is all. This is precise and simple. This is all. I've chosen a model. This is actually choosing the model. I have chosen. I've chosen the model to be linear regression. Okay. The first thing that is I have done. Please recapitulate the procedure. You clean the data.
Excuse me, sir.
Yeah.
I have one doubt. In the 13th line, its output is right below the line, right? That is 354 is the X train, and 13 is the column number or the features that we have taken. Then what about the Y train?
Excuse me, you're talking about the 13th cell, right?
Yes,
this
yes,
one.
yes.
Okay, tell me now. It's about the shape. It's a number of rows, number of columns.
Okay. What about that Y value, Y train, and then there is no value for the column or the features?
Yeah, because it's one dimensional.
Okay.
If it's two dimensional, then there is an X, there is a row and a column. If it is only one dimensional, then it is simply not having any number of columns. So that's what it means. Okay.
Okay.
So there are. It's simply that corresponding to the 315 observations of AX, you have 354 values, the house values. These 354 represents 354 different houses. Okay, and these 354 essentially here represents the 354 house values. They're just numbers. You can store it as a single array, a one-dimensional array, and therefore you don't require a column for that.
Okay,
Sorry,
okay.
right. Okay, that's it. And now I have chosen the model. Here I have, this line basically is choosing the model, and here I'm basically training the model. So with scikit-learn, it's just about calling a line. You don't have to do anything. It's simply computer does the training. Okay, so now I can just run. I'm basically training. The training has been done. And now once the training is done, I can use the training to predict given an X value. Okay, what will be the corresponding house value. I have done both for the, typically you don't do it for the training data again. You don't, this part is just for academic interest, I mean, just for illustration, but typically you don't do any prediction on the training data because training data is exclusively used for fitting and not for doing any prediction. Okay, please don't do that. I've just for academic sake, I've just wanted to know how much error is actually there. But you don't have to worry about this. What matters is what happens to the test case. So I give as input, the input text is given. A regressor is the regression object dot predict. It predicts given a new test set. It predicts what is the output of that, a prediction. So this white test predict is the house values predicted by the system. Okay, and white test is the one that you already know what are the house values. Let us see how much error is actually there. What is the mean square error between white test and white test predict? Okay, I just take the square root of that and I find that it is 4.61. So there is an error of something around $4.61,000, when it comes to predicting the house values. So is the procedure clear? I don't want you to be too much bothered about how much accuracy does it produce, but rather you should be rather looking at the procedure of what I have actually done. You will be almost doing the same procedure for every process that you basically do. Okay, so once again, recapitulating, the first thing that you do is missing value filling, which is done using imputer fit transform. It fills the missing entries with the mean values. Here in this case, because I've chosen mean here, I could have chosen median or mode also. And then there are no more missing values in it. Then I scale it to 0 mean 1 variance variables. So then here exactly is the scaling happens. Here I have just created an instance of the scaler. Actually here the scaling happens here. Okay. And then just to check, I have just displayed the mean here. You can see it's almost 0 everywhere because it's 0 mean. Now then I want to split it into training set and testing set. So which is done using train test split. These are all part of this scikit-learn package. Don't worry about that. Here I have chosen 30% for testing my developed model. And then that is here in this case 354 goes to the training set and 152 goes to the test set. And then I choose the model. Here I have chosen linear regression to be the model. I do the training here. Okay, and then I do prediction on the test set. The test root mean square error that I get is 4.61. Okay, I have done something for ridge regression also. Ridge regression is again linear regression, but it's called regularized linear regression with something called an L2 penalty. But so we are not bothered about that. That is about regularization, and that's a different issue. That's more connected with something that you might be knowing about. That's something called overfitting, and that is one purpose why you have ridge regression. Another purpose is that sometimes the data metrics might be ill-conditioned, where you need to make it a well-defined problem, in which there are many purposes why you call it. Let's not go into that. At least make sure that you are okay with up to this point. Are you clear about what I have done here? Am I clear with what I have done here?
Yes, sir.
Yes, sir.
Okay. So now I'll just stop with an example of a classification case also, and then I'll stop. I had an MLP and a CNN. I think the time is running I'm running short of time, so I'll just try to go through a classification case. So I have used something called a PIMA Indian diabetes data set, wherein you have, basically that's also available. Actually, I downloaded it from the net, so you can collect this. This is an open source data, so you can just download this. And then I have read it using, there is a very important package called Pandas, which is used for storing data frames. You can display it as, tables, wherein you have a number of features here, okay? Pregnancy, plasma count, blood pressure, skin millimeter, insulin dosage, body mass index, and so on, age, and so on. And target is whether the person is diabetic or not. Okay, that is what you have to predict. Given these parameters, these 8 parameters, you have to determine whether the patient is likely to be diabetic or not. Okay, so what I have done is I have just again I have to do here. I have to clean the data, fill in with missing. If there is any missing value, please do fill in, and then standard scaler to transform the data to 0, 1 range, 0 range, 0 mean, variance 1 range. And now I am going to declare a logistic regression, which is a classification algorithm. You can just Google it. This is a classifier instance. This is very important. It's very important to know about logistic regression, because most of you students and faculty will be doing your project in deep learning, and logistic regression typically happens to be the last layer of almost all deep learning classifiers. So please do understand, try to go to the theory of logistic regression, what exactly it is. For the time being, since I don't have much of time left with me, I'm just going to say that it is a binary classifier. Here it is a binary classification problem, because the class is either 0 or 1, whether it is diabetic or not. And there are 768 instances of available with you, data rows available with you. I have displayed only 5 of them here, but you have 768. I create a classifier instance. I split it into 80-20. So the test size is 20%, and the training size is 80%. Okay, 80. That's 80:20 split is what I have done. Okay, and once that is done, I can do the training here. Again, the procedure is exactly the same with scikit-learn. It's simple. We create an object instant, call the fit function inside the instant. The fit method of the object of the class. This is the training happening here. Okay, it just happens so. And now you can predict. You just do the prediction. You give the test data, and then you make the prediction, and then you will be having the accuracy score. This is white test that's available with you. You know whether they are diabetic or not available with you, and this is what your system predicts. You give it to the accuracy score function, which is also part of the scikit-learn metric, which I give here, and it gives you the accuracy score, which happens to be nearly 76% of the time, which is not a very high percentage. There is enough scope for further improvement, definitely. And accuracy is one metric. So whenever you do a classification, you should not stop with accuracy score, because accuracy score is always not the best way to express the performance. You should compute some other metrics also, like precision and recall, and that's about how many of true positives and false positives and so on are actually there. Those measures are also have to be there for you to clearly have an idea of how well your system is performing. So given this, I get something around 76% and a precision of 67 and a recall of something around 63. So which is not a very high performing system. There is enough scope for much greater performance. And here again, logistic regression is also again actually a linear model of classification. So there are some parameters associated with the model. The parameters are classifier.coef, coefficient, and an intercept. That is Wx plus B. B is intercept, W is coef. So that is W is here. These are the parameters of the model. And by calling the fit function, what it actually did is it figured out a nice W and B. That is what it has actually done. Okay. So this is about classification. An example of classification. In the same way, you can actually find out the parameter. Maybe I might have found out the parameters there. Yeah, here. The linear regression case also I have found out coef is the parameter W. Wx plus B is the, the model. So B is here 22.496 and here W is a 13-dimensional vector. In the classification case, it will be 8-dimensional because there are 8 features. You can count them: 1, 2, 3, 4, 5. 1, 2, 3, 4, 0, 4, 5, 6, 7, 8. 8-dimensional features, and B is the intercept. So now I think I have come to a conclusion of what I've actually prepared. I've written a small convolutional neural network also, but I think I don't have the time to discuss that. And a small multi-layer perceptron too, but I don't think I have the time. I think I have crossed my the time that was given to me. Sorry for that, in fact, for taking another 10-15 minutes more. Thank you. Thank you for your, if you have any questions, please do ask. I'm ready to answer if it is within my knowledge. And
If anybody have any doubts or queries regarding the section, you can use this time. Anyone?
Okay, no doubt, Naja.
Okay. So I think nobody have any doubt. So thank you, sir. Thank you so much for taking this section. This was amazing and really insightful. And for presentation on the power that data holds, and as well as the value and challenges associated with the data analytics. And I also appreciate each and every one of you for your active participation. Thank you everyone. And the certificate, the link will be provided in the chat box. You can fill that. Once again, thank you.
thank you. Thank you for your patient listening. Thank you. Can I leave, Surmi madam? Can I leave now?
Yeah, yes, sir. You can.
Yes, sir.
Thank you, sir, for the wonderful session. Thank you for the information.
Thank you, sir.
Can I leave, Surmi madam? Can I leave now?
Yeah, yes, sir. You can.